In this video, we are going to talk about the best compromise infeasible design. My name is Christian Aparicio. If you have any questions, whether you're a student or professional engineer, feel free to send me an email at this address and I'll go ahead and get back to you. And again, the support I provide is exclusively for Nastran Solution 200. So let's go ahead and get started. This is, again, one of the most important videos you will watch when it comes to optimization with Nastran. So let's go ahead and jump into it. We're going to be dealing with the very familiar example from the previous videos. In the previous video, we included this constraint. We said that anything outside of the ellipsoid is an acceptable design. In this video, what we are going to say is that any design that's inside of the green ellipsoid and any design that's inside of the red ellipsoid is a valid design. Now, you might be scratching your head at this point and saying there's no design that is inside both the green and the red ellipsoid. And that is true. This is why this is known as the best compromise infeasible design. When you try and give the optimizer a problem like this, it discovers that no solution is possible and then stops and it tells you what happened. Here we can visually see what happened. The optimizer starts at the initial point of 3, 4. It tries to go towards the minimum. It eventually finds out that I cannot be in both the green or the red ellipsoid, so I'm just going to stop right at the middle. This is the best I could do. I'm going to stop there. That's what the optimizer is doing. So let's look at the equations we'll be discussing. F will be the same objective equation from before, y1 squared plus y2 squared. G1 is the same equation from a video prior. We're going to introduce a new curve or equation, G2. G2 is going to be represented by this red ellipsoid, or rather, this red ellipsoid is representing this inequality. G2 is always less than 1. So here we're going to say that, again, the design is valid as long as G1 is less than 1. So if you're inside of the green ellipsoid, and G2 is less than 1. If you're inside of the red ellipsoid, remember, a design that satisfies both of these inequalities does not exist. You cannot be in the green ellipsoid and the red ellipsoid. That is not possible. The optimizer discovers this, it stops, and it tells you it cannot do it. So let's go ahead and discuss how to do this in Nastran. I want to show you what the error message looks like, and then I want to show you how to fix this message. So let's go ahead and start with the starting files. Feel free to go to the video description, download the solution files, and follow along. So let's go ahead and download the solution files from before, and you'll see that I already have my equation objective defined. I already have my equation constraints defined, so that's here. Now, this expression, R1 if you will, is my G1 function. We're saying that y1 squared plus y2 squared is, or y2 over 2 squared should always be greater than 1. If you look back at the plot, the upper bound is actually a value of 1. So let's go ahead and delete this one and move it to the upper bound. So this equation should always be less than 1. Let's go ahead and create the second equation constraint for G2. And here we'll go ahead and type that in. Let me go ahead and see where my plot is. So here the equation is open G1 minus 2.5 close squared plus y2 divided by 2 minus a 0.75 squared. And then again, the upper bound for the inequality is 1. So this is representing the two ellipsoids that you see here. We're saying that whatever the design variables are, it should be within the green ellipsoid and it should be within the red ellipsoid. this is the same as satisfying this inequalities. Again, this is not possible, so let's go ahead and see what happens with the optimizer. So here, let me go to the exporter. Before I move on, you'll get this message saying that you've created a new constraint, but you have not assigned it to a subcase. The subcases are known as load cases in some instances. Right here, it's a warning me telling me that I have not applied the constraint to the problem. So let me go ahead and mark a checkbox. Now this constraint is assigned to the problem. Let's go ahead and download the zip file. Let's go ahead and confirm to keep it. And let's go ahead and extract the contents and perform this optimization. Now remember, this optimization problem statement does not have a solution. You cannot satisfy the first and second equation constraints. So we'll go ahead and start the optimizer, and then we'll go ahead and see what Nastran does in this scenario. What Nastran ends up doing, it ends up finding the best design between the constraints. So here, let's go ahead and look at what we have here. So the message here reads, run terminated due to hard convergence to a best compromise infeasible design. So let's go ahead and see what the plot shows. So like before, we started at a value of 3, 4, a surface value or an objective value of 25. We go down to a value of 6.25. At this point, the optimizer has discovered that it cannot satisfy both constraints. It ultimately lands at a value. Let me see if I can show what this value is. It ultimately lands at a value of 1.26, 0.755, objective value 2.16. So here, the objective is 2.16 here. The design variables for y1 and y2 are 1.26 and 0.755 respectively. So here we can confirm this is what happened. Now, let's talk about the normalized constraints. Here you can see we started at a normalized constraint of 12. So that means our first design is violating the constraints. And that is because if you look at the plots, you can see that the initial point is outside of the ellipsoids. If you evaluate these inequalities, you'll find that G1 is actually greater than 1. G2 is greater than 1 also. This is why the normalized constraint value is negative. So here we have, positive 12. It then tries to find a solution that satisfies the inequalities. And here you can see that ultimately it finds out that it can never hit a normalized constraint value of 0. If you have a normalized constraint value that's negative, that means you're satisfying your constraints. But here it ends up finding out that the best it can do is obtain positive normalized constraints. Positive normalized constraints means you're violating one of your constraints. The optimizer eventually finds out that I cannot do any better. I must have hit a best compromise infeasible design. So now let's talk about how to fix this. What do you do in such a case? So here I will go ahead and walk you through the process. It's very explicit. This is because you may encounter this in your own example. And so I want to discuss how to fix this. Now, here I'll just go ahead and say what you should do. If you ever encounter this error message, what you should do is find out which constraints are being violated and relax the constraints. Here as an example, I'm going to take this red ellipsoid, this G2 inequality rather, I'm going to relax the constraint. I'm going to say G2 should be less than 3. By saying that, this expands the red ellipsoid. So anything between the red and green ellipsoid is a valid design. When we run this example, it is able to find a solution in the intersection that you see here. So here, it's a very small sliver between the green and red ellipsoid. This region of designs gives you a design that satisfies both G1 and G2. And this is ultimately where a solution is found for the minimum. So now, let me walk you through the process of how to discover this. If you go to the results section and click on this app, F06 for responses, let's go ahead and select the F06 file that was produced during the last optimization. Remember, this is the one that produced the message run terminated due to hard convergence or at a best compromising feasible design. So here, let's go ahead and plot the maximum constraint for each design cycle. That would be this top right hand icon. So this is where I can see the following. These both values with the double asterisk, these correspond to the normalized constraint value. So here we have a value of 12. Here we have 1.2 times 10 to the 1. So this is 12. The next value is 2.25. So that would be here. The next value is 0.75. So here, that's what you see here. So this table is corresponding to the various values of the normalized constraint plot. So this is where you can see which values are being violated. Here you see that R1 is being violated for both the initial 1, 2, 3, and the fourth design cycles. Let's go ahead and mark the violated constraints. This can give you more information about which constraints are being violated. Now, here, G1 is evaluated at 13 at the beginning. G2 is the value of 1.8. You can see it's violating the inequality. It's greater than 1 here, here, and here. What we're going to do is expand the upper bound for this inequality. We're going to say that the value is now 3. Let's go ahead and do that now. So back in the web app, let's go to the constraints. Let's relax the constraint by increasing the upper bound. And let's go ahead and download a new version of the zip file. Remember, the key here is relaxing the constraints. Let's make it a little easier for the optimizer to perform the optimization. So just in case you have any questions, I'll go ahead and show my email again. Feel free to contact me if you have any questions. I'll definitely get back to you with a reply as soon as I can. Let me go ahead and move this to the bottom right. And let's go ahead and start the optimization. Now, let's go ahead and look at the surface plot. Since we relax the constraints, in this case, we see that the optimization has gone through successfully. We have this message, run terminated due to hard convergence at an optimum. So that's very good news. Let's visually look at what happened. The optimizer went towards the minimum. So here you can see it's going towards the minimum. It eventually finds this region that has solutions that satisfy the inequalities. Remember that anything inside of the green and red ellipsoid are satisfied constraints. If we look at this first and second design cycle, we see that we are only inside the red ellipsoid. We are not inside of the green ellipsoid. So this first design is violating the constraint. The second design cycle is violating the G2 inequality. If we look back at the plot, this is what we see. The normalized constraint value for the initial design is positive. The second design, or the first design cycle rather, the normalized constraint is also positive. Positive means that you're violating at least one constraint. Then here we have values very close to zero. Values close to zero or values close to negative, or rather that are negative, indicate that you're satisfying your constraints. For design cycles 2, 3, 4, 5, and 6, you are at a solution that's satisfying your constraints. So here in this case, you're literally inside of both the red and green ellipsoid, and this is where you're satisfying the inequalities. So now let's go ahead and take a quick look at the design variables. We start at a value of 3, 4, and we ultimately land at 0.9 and 0.18912. Now, the one thing I want to stress here again is that if you ever encounter this message where you have hard convergence to a best compromising feasible design, use the responses app to track down which labels are being violated. Once you track down that here it's R1 and R2, think about which ones should you relax the constraints for. Here I went ahead and found out that R1 and R2 are being violated. Here I'm just going to go ahead and try relaxing constraint R2. So I went in the web app. Before it was a value of 1, I then increased the value to 3. When I tried this, I finally achieved a hard convergence to an optimum. So this, again, is the same as going from the red ellipsoid here, increasing the upper bound so that then you have solutions that are possible for the equation constraints. So again, this is perhaps one of the most important videos you're going to watch. You might be applying hundreds of stress constraints, hundreds of displacement constraints. If you're dealing with dynamics, you might be applying constraints on the natural frequencies. With so many constraints, you might eventually hit this what's the word I'm looking for? You might be looking for this impossibility. You might pose a problem that does not have a solution. Nastran tells you there's no solution, so then it's up to you to track down, out of all the constraints, which ones should you relax so you can achieve a possible solution. In the next video, I'm going to talk about something more complex. This is global optimization. So I think at this point, I'll go ahead and pause, and I'll see you in the next video.